So I'll take a balloon and rub it on my hair and get it pretty chargy, and I can see the balloon obviously has a pretty good charge on it at this point. I'll bring it near the charged rod, and then I can get an upward force on it. If I hold it stably there, when I played with this before, I can get it to stably float at a distance of about 15 centimeters from the rod. That's enough information to be able to calculate how much charge is on the balloon. Let's take a look at a problem that addresses that very issue. Let's take a look at the problem. A rod with charge plus 350 nanocoulombs is being used to levitate a charged balloon which has mass 2.0 grams. The balloon is being held stationary 6.0 centimeters below the charged rod. Question: what is the approximate charge on the balloon? Well, this of course looks just like something we've seen previously. We saw a situation where a charged rod was being used to levitate a balloon, and now we have some details. The rod has a charge of plus 350 nanocoulombs. The balloon has a mass of 2.0 grams, and those actually match what you saw in the introduction. The only difference is this. We're going to consider a case where the balloon is being held stationary about 6.0 centimeters below the charged rod. So that's a little bit different than the setup that you saw in the introduction. But the details are about the same. Now, there's another piece of the statement that's interesting to consider here. We're asked to find the approximate charge on the balloon, and that's crucial because we know we can make an approximate calculation, and that's important because we're given a rod that has a charge on it, okay, and it's being used as a levitated balloon. Neither of those are simple shapes, but since we're doing an approximate calculation, we're going to assume that everything looks like point charges, and so we're going to assume we can basically do a Coulomb's law calculation where we've got two charges, charge Q1 and a charge Q2. We've got a charged rod up here at the top. We have a balloon down below, and there's a distance between them. And the distance between them is 6.0 centimeters. That's the R in our Coulomb's law expression. And of course, we need to put that in meters. So 0.060 meters. We're going to treat the problem this way. It's a Coulomb's law problem. Now we have some additional information. We know that the upper charge is the rod and has a charge of positive 350 nanocoulombs. So it's positively charged. Q1 we can write as positive 350, and that's nanocoulombs. So 350 times 10 to negative 9th coulombs. That's my charge on the top one. We're being asked to find the charge on the balloon. And to do that, we have to consider the forces on the balloon. Now, a most important thing before we can figure out what direction to put the forces in is we need to consider this. What is the sign of the charge? What is the sign of the charge on the balloon? So the balloon's sitting down here. It's levitating. It's not going anywhere. What is the sign of the charge on it? We'll give you some choices. Well, now think about the forces that are acting on the balloon, okay? There's a downward weight force. We know that that has to be the case. We know that there has to be a downward weight force. And since it's a force, and that's kind of a chapter 5 thing, I'm going to draw it in red. Here we go. So there's a downward weight force. We know that that's true. And if the balloon's levitating, if it's not going anywhere, there has to be an upward force. And the upward force, we're just going to take to be equal to, it's the electric force. It's provided by the electric attraction of the rod. So if the balloon is being pulled downward by the weight force, it's being pulled upward by the electric force, it's an attractive force to the charged rod, and so therefore the balloon has to have a negative charge. So that's the first piece of the puzzle. As we're thinking about solving this problem, we can say this, that the charge on the balloon is definitely negative. That's going to be the first piece of the puzzle. Now, we're going to have to consider the relative magnitudes of these two forces that act on the balloon. Okay, the weight force is directed downward. The electric force is directed upward. Before we can consider the magnitudes of these two forces, we have to answer an important question. What can we say about the net force? What is the net force on the balloon? So that's taking you back a ways, thinking about forces. That's back in chapter 5. So think about that for a minute and answer, what is the net force on the balloon? We'll give you some choices. Well, the balloon's not going anywhere, so that tells us that the net force is equal to 0. And if the net force is equal to 0, that tells us that we can say that the magnitude of the weight force and the magnitude of the electric force are just equal to each other. I can equate the magnitudes of those two forces because the weight force pulls down, the electric force pulls up. And I can write that as an expression. The magnitude of the electric force is K times Q1 times Q2 divided by r squared, where r is the distance between the two charges. The magnitude of the weight force is just equal to m times g. What I'm trying to solve for in this problem is the approximate charge on the balloon. So since that's true, I'm going to take this problem and I'm going to solve for Q2, which is the charge on the balloon. And if I do that, I get the following. I get Q2 is equal to m times g times r squared divided by k times Q1. Now take a look at these numbers, okay? We know every number here. We know what r is. Okay, r is the 0.060 meters. We're given that. We know what the mass is. The mass is 2.0 grams. Now we're going to have to put that in kilograms. 2 grams is 0.0020 kilograms. That's going to be important. So I've got the mass. I have the radius. I know what g is. G is 9.8 meters per second squared. I also know what k is. So I've got g. I've got k. K is that electrostatic constant. That's the 9 times 10 to the 9th number, which we've used regularly. And we also know what Q1 is. Okay, so we know R, I know M, I know G, I know K, I know Q1. I have everything I need to solve for Q. So I can go ahead and take all those numbers that I'm given, and I can solve for Q2. Now, I'm going to write my final expression for Q2, incorporating what we know about the sign of the charge on Q2. We know that this is a negative charge. So I'm going to write this Q2 is equal to negative, and then I'm going to compute the magnitude from this expression right here. And the magnitude that I get is 22 nanocoulombs. Except we were asked to figure out the approximate charge. And actually it doesn't make sense to give this as a two significant figure answer because we're treating these both as point charges, and the rod and the balloon aren't point charges. So we'll list our final answer to one significant figure with the correct sign, and we're going to say this. The charge on the balloon is approximately equal to 20 nanocoulombs. Next step is to look at our answer and see if it makes sense. Let's take a look at our results and see if it makes sense. Okay, first off, this little wand gets charged up positively. And when I touch it to that piece of mylar, and it's got aluminum on it, it's a conductor, it gets a positive charge. We said the balloon was negatively charged, so the balloon should attract that piece of mylar, as in fact it does. So the sign of charge is correct. How about the magnitude of the charge? Well, we came up with a number of about 20 nanocoulombs. I want to make a couple points about this. A more careful measurement shows that that's about right for the balloon. 20 nanocoulombs, very reasonable result. You'll notice when you look through the textbook, when we charge up objects, that's a typical kind of number which we use for charged objects. And the reason is because when you charge objects by rubbing, things which get a good static charge, like a balloon rubbed onto your hair, that's the kind of number we use, and it's because that's about the number that you get if you charge something up. We've taken great pains every step of the way in the book to make sure that our numbers are realistic. And so the number that we get is realistic as well. Not a huge surprise. Physics is about the world around us.